Hello friends, I am Dr. Prof.Chishty and I am teaching physics to BSc second year students. My today's topic is solid state physics, and in this solid state physics let us start with the fundamental concepts of the solid state physics, that is the crystal structure. So the material can be divided into two parts according to their arrangement of the atoms or the molecules. One is gem and another is crystal. Gem and crystal. Okay. Gem is those material in which the arrangement of the atoms or molecules are haphazard. They are not in the regular fashion. Molecules are randomly arranged. For example, we can say that glass is a gem. Glass is a gem. While we can say that the diamond is a crystal. So in a crystal, the arrangement of the atom, large number of the atoms are regularly arranged. Infinite number of the atoms are regularly arranged, periodically arranged, and they form particular shape. So a periodic arrangement of the atoms or the molecules in a material is called as the is nothing but a crystal. So to understand the crystal, for example, I can give the example of the crystal as diamond is a crystal, single atom crystal, diamond. Similarly, NaCl is a crystal. NaCl is a crystal. Calcium carbonate is a crystal. CaCO3, calcium carbonate is a crystal, while glass is a gem, rubber is a gem, okay, wood is a gem. So other materials are gem. So we can categorize the material into two parts. One is the gem and another is crystal. So now let us understand about the crystal. What is a crystal? To understand the crystal, we can study about the lattice and the basis. What is the lattice and basis? So let us see that what is lattice. Lattice is nothing but the arrangement of the points in a regular fashion. Large number of the points, infinite number of the points which are arranged in a regular fashion is called as a lattice. For example, these are the points which are arranged in a regular manner, and these points are called as the lattice points. Each point is called as a lattice point. And when we put some atoms or the molecules on this lattice point, then it is called as a basis. For example, I am having the seating arrangement in a class. So every seat of a student will serve as a lattice point, and when a student sit, a student occupy on that seat, then a student is said to be basis. So when basis or the atom or the molecules occupy a seat or occupy a lattice point, then it is called as the basis. So these are the basis. So we can say that the atoms or the group of the atoms or the molecules or the group of the molecules occupy each lattice point, and lattice plus basis, lattice point, lattice plus basis combine to form crystal. They are combined to form the crystal structure. A lattice and a basis combinedly form as a crystal. So in a crystal there is regular arrangement of the atoms or the molecules on each lattice point. This arrangement may be in one dimension, they may be in two dimension, or they may be in the three dimension. For example, I consider only one line of the atoms of the crystal points and the basis. So this one is called as the one-dimensional crystal. 1D, one-dimensional crystal means that each points are arranged either on the x-axis or on the y-axis or on the z-axis. if suppose the crystal points, the lattice points are arranged along the x-axis as well as the y-axis, x-axis as well as the y-axis, it means that they are going to form a plane. X-axis plus y-axis going to form a plane, and when there is formation of a plane, we say that it is a plane two-dimensional lattice, or plane lattice, or two-dimensional lattice, or two-dimensional crystal. Lattice may be two-dimensional when bases are occupy on each lattice point, then the crystal is called as the plane crystal or a two-dimensional crystal. If suppose these points are arranged in the three dimensions, in the three dimension means in the space also, along the x-axis, along the y-axis, and along the z-axis, then we will get a structure in the three dimension, means the lattice points are all occupy the one dimension, means along the x-axis, along y-axis, and along the z-axis. They are having the particular volume, not the area but volume. So we say that such a lattice is called as the space lattice. Space lattice. So friends, we studied about the one-dimensional lattice, plane lattice, and the space lattice. In one-dimensional lattice, the lattice points are arranged on the only x-axis or y-axis or z-axis, along any one of the axes. In two-dimensional, lattice points are arranged along the x-axis and y-axis, while in the three-dimensional or the space lattice, the points are arranged on all the three axes, x, y, and z axis, and they are having the volume. Okay, so now the lattice points or the crystal atoms can be arranged in different manners. So let us see how the atoms can be arranged in a regular fashion. So lattice points can be arranged in a square wave, square form, in this manner, going to form the square lattice. All the atoms means angle between, if we draw the two perpendiculars, here the angle is 90 degree. So we say that it is the square lattice. Then there may be oblique lattice points. The lattice points are situated in oblique manner. So it is the oblique lattice. Okay. Or the lattice points, here it is oblique, here it is square lattice in two dimension. Or we can say that atoms may be arranged in this fashion also. Some lattice points, then another lattice points will be situated at the center of each lattice point. You can see the arrangement. Okay. They are equally spaced, identical points, equally spaced, and they can be seen in the same environment. The environment surrounding to all the atoms may be same. When these lattice points are occupied by the basis or the group of the atoms, then there is formation of the crystal structure. Okay. So crystal structure may be one dimension, maybe two dimension, or maybe three-dimension crystals. Okay, so now let us study about the translation vector. What is the translation vector? How we are going to translate the lattice points. So here let us consider here the lattice points which are situated here, equally spaced. They are equally spaced. Equally spaced points. Okay. Now I am having I want to translate the lattice points about any one of the point. Suppose here I am having this point O. Now I will draw a vector. Suppose vector A, vector A1. Okay, and I will join the another lattice point by vector b1. Vector b1. So we can say that the translation vector t is equal to n1 a1 plus n2 a2. Sorry, n2 b1, where a1 and b1 are the vectors drawn in the direction of the molecules or the atom or the lattice points, and n1 n2 are the integers. They are integers. This point is suppose r and this point is suppose r dash. So if the surrounding is identical, the point O should be seen identical, should be seen same, unchanged from the point R, vector R, or from the R dash. Okay. Now, if the lattice is in 3 dimension, means I am having 3-dimensional lattice, then we can write the translation vector as n1 a1 plus n2 a2 plus n3 n1 a1 plus n2 b1 plus n3 c1, where a b c are the fundamental vectors. This a b a1 b1 c1 are called as the fundamental vectors, and n1 n2 n3 are called as the integers. They are called as the integers. But the point O about which the lattice is seen or the other points are observing, the point O should remain unchanged with respect to either R or R dash. So if I want to write the equation about the, by taking the vectors, fundamental vectors as A1 and B1, and I want to translate it for R, then what I will do, I am having fundamental vector A1 here, fundamental vector B1. Now I will draw a line, a vector from R to R dash, so that R dash vector can be written as vector R plus vector T. This vector is parallel to B, so I can write here it is B1 vector. It is same as B1. So I can, for T, I can write here 0 A1, means A1 is 0 plus 1 B1, 1 B1. For this one, A1 is 0 here, and 1 B1 from R to R dash, from R to R dash. Therefore, vector R dash can be written as R plus 0 A1 plus 1 B1. So it is the translation vector from point O to R. Point O to R means I have to translate in some another form. Now if suppose I am having A2 and B2, the fundamental vectors A2 and B2, and I am translating it about the R dash. So here it is A2, this will become A2, and this will be here B2. Now what I have to do, I have to find again the value of T, that is R dash is equal to vector R plus T. Okay. Now I will find the value of T. Value of T here is, now I will extend this up to half A2, half A2, it is half A2, this one is A2, this one is A2, so it is half A2, and I have to translate it from the upper side, that is from here it is half B2. This one is half B2. From this point to this point, it is half B2. This distance is half B2. Total is B2. This distance is half B2. Total B2, half B2. If it is half B2, this is half B2. If it is half A1, then it is half A1. Okay. This distance is half A1. So I can write the value of translation vector T as half A1 or A2 plus half B2, where A2 and B2 are the fundamental vectors. So value of R dash is equal to vector R plus half A2 plus half B2. So we can say that if the value of N1 and N2 in the translation vector, for example here it is 0 and 1 or 1, 2, 3 integer, then it is primitive. If the value of n1 and n2 in translation vector are integer, for example 1, 2, 3 and so on, then it is called as a primitive vector, translation vector. If the value of n1 and n2, for example here it is half and half, half is non-integer, then the lattice, the vector is called as the non-primitive translation vector, non-primitive translation vector. So we can translate any point, any lattice point about any given point, so that that point should remain unchanged, and it is known invariant. So it is called as the vector, translation vector. We can draw the translation vector for explaining this. So this is all about the translation vector. Thank you.